ਸਾਰੇ ਆਬਜੈਕਟਸ ਇੱਕ ਰੇਂਜ ਆਫ ਫ੍ਰੀਕੁਐਂਸੀਜ਼ ਲਈ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਰੇਡੀਏਸ਼ਨਸ ਐਮਿਟ ਕਰਦੇ ਹਨ। ਰੇਡੀਏਟਡ ਫ੍ਰੀਕੁਐਂਸੀ ਸਭ ਤੋਂ ਜ਼ਿਆਦਾ ਆਬਜੈਕਟ ਦੇ ਟੈਂਪਰੇਚਰ ਉੱਤੇ ਡਿਪੈਂਡ ਕਰਦੀ ਹੈ। ਇਸ ਪਿਕਚਰ ਵਿੱਚ ਗਲੋਇੰਗ ਮੈਟਲ ਪੀਸ ਪ੍ਰਾਇਮਰੀਲੀ ਸਪੈਕਟਰਮ ਦੇ ਇਨਫਰਾਰੈਡ ਪਾਰਟ ਵਿੱਚ ਰੇਡੀਏਟ ਕਰ ਰਿਹਾ ਹੈ, ਪਰ ਇਹ ਇੰਨਾ ਗਰਮ ਹੈ ਕਿ ਇਸ ਦੀ ਰੇਡੀਏਸ਼ਨ ਦਾ ਇੱਕ ਸਿਗਨੀਫੀਕੈਂਟ ਪੋਰਸ਼ਨ ਵਿਜ਼ੀਬਲ ਰੀਜਨ ਦੇ ਰੈਡ ਐਂਡ ਵਿੱਚ ਪੈਂਦਾ ਹੈ।
Dear students, spectrum of hydrogen atom ਦੇ ਇਸ ਟੌਪਿਕ ਵਿੱਚ ਅੱਜ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਤੁਸੀਂ ਕਦੇ ਨਾ ਕਦੇ ਕਿਸੇ ਸਟੋਵ ਜਾਂ ਇਲੈਕਟ੍ਰਿਕ ਹੀਟਰ ਦਾ ਹੀਟਿੰਗ ਕੋਇਲ ਤਾਂ ਦੇਖਿਆ ਹੀ ਹੋਣਾ ਹੈ। ਵਰਕਿੰਗ ਕੰਡੀਸ਼ਨ ਵਿੱਚ ਇਹ ਅੱਖਾਂ ਨੂੰ ਲਾਲ ਨਜ਼ਰ ਆਉਂਦਾ ਹੈ। ਜ਼ਿਆਦਾਤਰ ਰੇਡੀਏਸ਼ਨ ਇਨਫਰਾਰੈਡ ਰੀਜਨ ਵਿੱਚ ਹੁੰਦੀ ਹੈ ਅਤੇ ਸਾਨੂੰ ਵਿਜ਼ੀਬਲ ਨਹੀਂ ਹੁੰਦੀ। ਇਹ ਤਾਂ ਸਾਨੂੰ ਪਤਾ ਹੀ ਹੈ ਕਿ ਮੈਟਲਸ ਵਿੱਚੋਂ ਬਲੈਕ ਬਾਡੀ ਰੇਡੀਏਸ਼ਨ ਹੁੰਦੀ ਹੈ ਅਤੇ ਇਹ ਸਾਰੀਆਂ ਪੋਸੀਬਲ ਫ੍ਰੀਕੁਐਂਸੀਜ਼ ਲਈ ਕੰਟੀਨਿਊਸਲੀ ਡਿਸਟ੍ਰੀਬਿਊਟਡ ਹੁੰਦੀ ਹੈ। This black body distribution or spectrum is characteristic of the atoms present in the metal and not of the spectrum of light that would be given off by a single isolated metal atom. To discuss about the light produced by an isolated atom, it is easy to discuss the spectrum of a gas instead of a solid. Atoms ਵਿੱਚੋਂ ਹਾਈਡਰੋਜਨ ਐਟਮ ਸਿੰਪਲੈਸਟ ਐਟਮ ਹੈ ਕਿਉਂਕਿ ਇਸ ਵਿੱਚ ਸਿਰਫ ਇੱਕ ਆਰਬਿਟਲ ਇਲੈਕਟ੍ਰੋਨ ਨਿਊਕਲੀਅਸ ਦੁਆਲੇ ਘੁੰਮਦਾ ਹੈ, ਜਿਸ ਵਿੱਚ ਵੀ ਸਿਰਫ ਇੱਕ ਪ੍ਰੋਟੋਨ ਹੁੰਦਾ ਹੈ। So, the spectrum of hydrogen atom can be modeled using relatively simple physical considerations. ਤੁਹਾਨੂੰ ਪਤਾ ਹੀ ਹੈ ਕਿ ਲੇਜ਼ਰਸ ਦੁਆਰਾ emitted radiation ਸਿੰਗਲ ਵੇਵਲੈਂਥ ਦੀ ਬਣੀ ਹੁੰਦੀ ਹੈ। ਐਮਿਟਡ ਰੇਡੀਏਸ਼ਨ ਦੇ ਸਭ ਤੋਂ ਜ਼ਿਆਦਾ ਕਾਮਨ ਸੋਰਸਸ ਯਾਨੀ ਸੂਰਜ ਜਾਂ ਸਨ ਅਤੇ ਲਾਈਟ ਬਲਬ ਡਿਫਰੈਂਟ ਵੇਵਲੈਂਥਸ ਦੀਆਂ ਰੇਡੀਏਸ਼ਨਸ ਕੰਟੇਨ ਕਰਦੇ ਹਨ। ਜਦੋਂ ਇਸ ਤਰ੍ਹਾਂ ਦੇ ਸੋਰਸ ਵਿੱਚੋਂ ਡਿਫਰੈਂਟ ਵੇਵਲੈਂਥਸ ਦੀਆਂ ਰੇਡੀਏਸ਼ਨਸ ਸੈਪਰੇਟ ਕੀਤੀਆਂ ਜਾਂਦੀਆਂ ਹਨ ਤਾਂ ਸਪੈਕਟਰਮ ਬਣਦਾ ਹੈ। ਜੇ ਇੱਕ ਗਲਾਸ ਟਿਊਬ ਵਿੱਚ लो ਪ੍ਰੈਸ਼ਰ ਤੇ ਵੇਰੀਅਸ ਗੈਸਸ ਫਿਲ ਕਰਕੇ ਹਾਈ ਵੋਲਟੇਜ ਅਪਲਾਈ ਕੀਤਾ ਜਾਵੇ ਤਾਂ ਡਿਫਰੈਂਟ ਕਲਰਸ ਦੀ ਲਾਈਟ ਐਮਿਟ ਹੁੰਦੀ ਹੈ। ਉਦਾਹਰਣ ਲਈ ਨਿਓਨ ਗੈਸ ਰੈੱਡ ਔਰੇਂਜ ਗਲੋ ਪ੍ਰੋਡਿਊਸ ਕਰਦੀ ਹੈ ਅਤੇ ਸੋਡੀਅਮ ਗੈਸ ਯੈਲੋ ਗਲੋ ਪ੍ਰੋਡਿਊਸ ਕਰਦੀ ਹੈ। ਜਦੋਂ ਇਸ ਤਰ੍ਹਾਂ ਦੀ ਲਾਈਟ ਪ੍ਰਿਜ਼ਮ ਵਿੱਚੋਂ ਪਾਸ ਕੀਤੀ ਜਾਂਦੀ ਹੈ ਤੇ ਰਿਜ਼ਲਟਿੰਗ ਸਪੈਕਟਰਾ ਵਿੱਚ ਕੁਝ ਥੋੜੀਆਂ ਜਿਹੀਆਂ ਵੇਵਲੈਂਥਸ ਹੀ ਪ੍ਰੈਜ਼ੈਂਟ ਹੁੰਦੀਆਂ ਹਨ। आओ एक एक्सपेरिमेंट देखते हैं।
Here in this experiment, we seal a low pressure gas in a discharge tube. On application of a high voltage between the ends of the tube, the gas emits electromagnetic radiation characteristic of the individual gas atoms. When we allow this radiation to pass through a narrow slit and a prism, we see a series of bright lines similar to magnetic barcodes as a result. The precise wavelength associated with each of these lines provides a sort of fingerprints identifying a particular type of atom, just as each product in a supermarket has its own unique barcode.
Different colors ਦੀ bright lines ਦਾ ਇਹ spectrum line spectrum ਕਹਾਉਂਦਾ ਹੈ। ਤੁਸੀਂ ਹੁਣੇ ਹੀ ਹਾਈਡਰੋਜਨ ਐਟਮ ਦੇ line spectrum ਦਾ visible part ਦੇਖਿਆ ਹੈ। ਹਾਈਡਰੋਜਨ ਐਟਮ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ spectrum ਦੇ infrared ਅਤੇ ultraviolet parts ਵਿੱਚ additional lines produce ਕਰਦਾ ਹੈ। First step in developing a quantitative study of hydrogen spectrum occurred in 1885 when a Swiss school teacher, Johann Balmer, used trial and error method which figured out a simple mathematical formula to calculate the wavelength of the visible lines of the spectrum. According to the Balmer's formula, the reciprocal of wavelength of a visible line is equal to r times 1 upon 2 square minus 1 upon n square, where n is equal to 3, 4, 5 and so on. Here r is a constant known as Balmer's constant and its value is 1.097 into 10 to the power 7 per meter. Each integral value of n in Balmer's formula corresponds to the wavelength of a different spectral line. Can you tell me what is the color of light that corresponds to n equal to 5? It's a simple calculation. On substituting the value of n equal to 5 in the formula, we get wavelength is equal to 4.342 into 10 to the power minus 7 meter or 434.2 nanometers. This is the wavelength for bluish color. The collection of all lines predicted by Balmer is known as Balmer series. Can you calculate the longest wavelength in the Balmer series? For the longest wavelength, we put the value of n as equal to 3. It gives the wavelength equal to 656.5 nanometers. This refers to red color. Similarly, can you calculate the shortest wavelength in the Balmer series? Now, if we put the value of n equal to infinity, it gives the shortest wavelength, which is equal to 364.6 nanometers. पर A wavelength electromagnetic spectrum ਦੇ ultraviolet portion ਵਿੱਚ ਆਉਂਦੀ ਹੈ ਅਤੇ ਇਸ ਕਰਕੇ invisible ਰਹਿੰਦੀ ਹੈ। Balmer ਨੇ ਸਿਰਫ visible spectrum ਲਈ ਇੱਕ mathematical formula ਦਿੱਤਾ ਅਤੇ ਇਸ ਦੀ ਕੋਈ theoretical explanation ਨਹੀਂ ਦਿੱਤੀ। 1913 ਵਿੱਚ ਨੀਲਸ ਬੋਰ ਨੇ ਆਪਣਾ ਹਾਈਡਰੋਜਨ ਐਟਮ ਦਾ ਮਾਡਲ ਪ੍ਰਪੋਜ਼ ਕੀਤਾ, ਜਿਸ ਵਿੱਚ ਹਾਈਡਰੋਜਨ ਦੇ ਸਪੈਕਟਰਮ ਦੀ ਥਿਓਰੈਟੀਕਲ ਐਕਸਪਲੇਨੇਸ਼ਨ ਦਿੱਤੀ। ਬੋਰ ਨੇ ਕਲਾਸੀਕਲ ਫਿਜ਼ਿਕਸ ਨਾਲ ਕੁਆਂਟਮ ਫਿਜ਼ਿਕਸ ਦਾ ਆਈਡੀਆ ਕੰਬਾਈਨ ਕੀਤਾ। ਆਓ ऑर्बिट ਵਿੱਚ ਇਲੈਕਟ੍ਰੌਨ ਦੀ એનર્ਜੀ ਦਾ ਫਾਰਮੂਲਾ ਦੇਖੀਏ।
According to Bohr's theory, electrons do not give off electromagnetic radiation when they are in an allowed orbit. Electromagnetic radiation is given off or absorbed only when electron changes from one allowed orbit to another.
Bohr then used classical physics to show that the energy of an electron in any one of these orbits is inversely proportional to the square of the integer n. According to Bohr, total energy of an electron in an orbit of radius Rn is equal to minus e square upon 8 pi epsilon naught Rn. On substituting the value of Rn, which is equal to n square h square epsilon naught divided by pi m e square, the equation for energy becomes En equal to minus m e to the power 4 upon 8 epsilon naught square n square h square, which he further calculated as minus k divided by the square of the number of orbit, where n is an integer also known as the principal quantum number and corresponds to different orbits. Here k is proportionality constant for hydrogen atom and it is equal to minus me to the power 4 upon 8 epsilon naught square h square, whose value is 2.18 into 10 to the power minus 18 joule or 13.6 electron volt. Hence, the energy of nth orbit becomes En equal to minus 13.6 upon n square electron volt. Since the principal quantum number n can have values 1, 2, 3 or so on, therefore, the electron in different orbits have some definite value of energy in different orbits. This is called the quantization of energy. You can notice that the energy of electron in a stationary orbit is negative, which indicates that the electron is bound to the nucleus and is not free to leave it. The difference between the energies of any two orbits is therefore given by the equation delta E is equal to energy of final orbit minus the energy of initial orbit, which is k times the difference of the square of the reciprocal of the orbit numbers, or it is equal to 13.6 times the difference of the square of the reciprocal of the orbit numbers. In this equation, both nf and ni are integers, where ni is the number of initial orbit, whereas nf is the number of final orbit. Planck ने deduce ਕੀਤਾ कि photons ਦੀ energy ਜਿਹੜੀ electromagnetic radiation ਦੀ comprised ਹੁੰਦੀ ਹੈ frequency ਦਾ ਇੱਕ function ਹੁੰਦੀ ਹੈ। ਇਸ ਕਰਕੇ ਜੇ ਇੱਕ falling electron ਕੋਲ ਇੱਕ defined energy ਹੋਵੇ ਤਾਂ ਇਸ ਦੇ corresponding ਇੱਕ defined frequency ਵੀ ਹੋਣੀ ਚਾਹੀਦੀ ਹੈ। Planck's equation ਦੇ ਅਨੁਸਾਰ ਇੱਕ photon ਦੀ energy ਇਸ ਦੀ frequency ਦੇ proportional ਹੁੰਦੀ ਹੈ। We know that the frequency is equal to the ratio of speed of light and the wavelength. Therefore, the expression for energy of a photon becomes inversely proportional to its wavelength. Therefore, when an electron falls or jumps from an orbit to another orbit, it emits or absorbs a radiation whose wavelength can be calculated using the relation according to which energy difference equals the energy of the photon. From the expressions for delta E, we get k into the difference of the square of the reciprocal of the orbit numbers equal to hc upon lambda. The inverse of the wavelength of electromagnetic radiation, that is, the wave number, is therefore directly proportional to the energy of this radiation. Bohr was able to show that the wavelengths of the light given off or absorbed by a hydrogen atom as the inverse of the wavelength is equal to k upon hc into the difference of the square of the reciprocal of the orbit numbers, which is further equal to RH into the difference of the square of the reciprocal of the orbit numbers. Here, RH is the Rydberg constant, which is equal to k upon hc and whose value is 1.097 into 10 to the power 7 per meter. It was the most significant accomplishment of Bohr's model, as the value of Rydberg's constant is same as that of the Balmer's constant. Balmer's series is not the only series of lines produced by hydrogen atom. Spectrum of hydrogen atom is classified into different series, which is known as the spectral series of hydrogen atom. Let's discuss these spectral series one by one.
In the previous experiment, we sealed a low-pressure hydrogen gas in a discharge tube. On application of a high voltage between the ends of the tube and allowing electromagnetic radiation to pass through a narrow slit and a prism, We have seen a series of bright lines on the photographic plate. Let us analyze these spectral lines. Series with the shortest wavelength has been observed by Lyman in 1906, and it is known as the Lyman series. All of lines in this series are part of ultraviolet portion of electromagnetic radiation. Formula for this series is wave number equal to Rydberg constant times 1 upon 1 square minus 1 upon n square, where n is equal to 2, 3, 4 and so on. Series with wavelengths greater than the Lyman series is the Balmer series. Most of lines in this series are a part of visible portion of electromagnetic radiation. Formula for this series is wave number equal to Rydberg constant times 1 upon 2 square minus 1 upon n square, where n is equal to 3, 4, 5 and so on. Series with wavelengths just greater than the Balmer series is known as the Paschen series. It was observed by Paschen in 1908. All the lines in this series are a part of the infrared portion of electromagnetic radiation. Formula for this series is wave number equal to Rydberg constant times 1 upon 3 square minus 1 upon n square, where n is equal to 4, 5 and so on. Series with wavelengths greater than the Paschen series is known as the bracket series. It was observed by Brackett in 1922. All the lines in this series are part of infrared portion of electromagnetic radiation. Formula for this series is wave number equal to Rydberg constant times 1 upon 4 square minus 1 upon n square, where n is equal to 5, 6 and so on. And the series with wavelengths greater than the bracket series is known as the Pfund series. It was observed by Pfund in 1924. All the lines in this series are part of infrared portion of electromagnetic radiation. Formula for this series is wave number equal to Rydberg constant times 1 upon 5 square minus 1 upon n square, where n is equal to 6, 7 and so on.
Let's have a look on an electron falling from a higher orbit to any lower orbit.
Here you can see that an electron absorbs some energy and jumps to higher orbit, which is the fifth orbit. When the electron falls from fifth to fourth orbit, radiation comes under the bracket series. When it falls from fourth to third orbit, it comes under Paschen series. And when it falls from third to second, it comes under Balmer series. When it falls from second to first orbit, it comes under Lyman series. Let us see what happens if the electron falls in different order. When the electron falls from fifth to fourth orbit, radiation comes under the bracket series. When it falls from 4th to 2nd, it comes under Balmer series. And when it falls from 2nd to 1st orbit, it comes under Lyman series. Let us see again, when the electron falls from 5th to 4th orbit, radiation comes under the bracket series. And from 4th to 1st orbit, it comes under Lyman series. In all these cases, one radiation comes under bracket series. Let us see, if the electron falls from 5th to 3rd orbit, it comes under Paschen series. When from 3rd to 2nd, it comes under Balmer series. And when it falls from 2nd to 1st orbit, it comes under Lyman series. If the electron falls from 5th to 3rd orbit, it comes under Paschen series, while when it falls from 3rd to 1st orbit, it comes under Lyman series. In these cases, at least one radiation comes under Paschen series. You can see, if the electron falls from 5th to 2nd orbit, it comes under Balmer series. And when it falls from 2nd to 1st orbit, it comes under Lyman series. If the electron falls from 5th to 2nd orbit, it comes under Balmer series. When it falls from 2nd to 1st orbit, it comes under Lyman series. Finally, if the electron falls directly from the 5th to 1st orbit, the emitted radiation comes under Lyman series.
Here we have seen a visualization for the different spectral series of hydrogen. Most important of these are the Balmer series, as it is the only part of visible spectrum. Do you know about H alpha, H beta and H gamma lines?
When an excited electron jumps down from 3rd orbit to 2nd orbit, it shows H alpha line. When the excited electron jumps from 4th orbit to 2nd orbit, it shows H beta line. When the excited electron falls from 5th orbit to 2nd orbit, it shows H gamma line. And when the excited electron falls from 6th orbit to 2nd orbit, it shows H delta line.
In general, the different series of hydrogen spectra can be represented as shown in this energy level diagram. It represents the total energies of an electron in different stationary orbits of hydrogen atom. However, in general, energy level diagrams can be useful for visualizing the complex level structure of atoms. Energy level diagrams are also useful to analyze the energies that electrons can accept and release as they transition from one accepted orbital to another. We know that the energy of an atom is the least when its electron is revolving in an orbit closest to the nucleus, that is, when n is equal to 1. This is the lowest state of the atom, called the ground state. The energy of the electron in this state is minus 13.6 upon 1 square, that is minus 13.6 electron volt. At room temperature, most of the hydrogen atoms are in ground state. When a hydrogen atom receives energy by processes such as electron collisions, the atom may acquire sufficient energy to raise the electron to higher energy states. The atom is then said to be in an excited state. For n equal to 2, value of energy of the electron in this state is minus 13.6 upon 2 square or minus 3.4 electron volt. It is equal to 1/4 of E1. It is called the first excited state. For n equal to 3, value of energy of the electron in this state is minus 13.6 upon 3 square, that is minus 1.51 electron volt. This is equal to 1/9 of E1. It is called second excited state. For n equal to 4, value of energy of the electron in the state is minus 13.6 upon 4 square, that is minus 0.85 electron volt. It is equal to 1/16 of E1. This is called the third excited state. It is clear that on increasing the value of n, En becomes less negative, and at n equal to infinity, E will tend to become 0. This shows that the energy is progressively larger in the outer orbits. From these excited states, the electron can then fall back to the state of lower energy, emitting a photon in the process. This also shows that as the excitation of hydrogen atom increases, in other words, as n increases, the value of minimum energy required to free the electron from the excited atom decreases. It also shows that the energy required to excite an electron in hydrogen atom to its first excited state is the energy equal to E2 minus E1, which is equal to 10.2 electron volt. Similarly, the energy required to excite an electron in hydrogen atom to its second excited state, that is E3 minus E1, is equal to 12.09 electron volt. These energy differences correspond to the wavelengths of light in the discrete spectral lines emitted by an atom as it goes from de-excitation or by the wavelengths absorbed in an absorption spectrum. ਅੱਜ ਦਾ ਟੌਪਿਕ ਕਨਕਲੂਡ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਐਕਸਾਈਟੇਸ਼ਨ ਅਤੇ ਆਇਓਨਾਈਜੇਸ਼ਨ ਬਾਰੇ ਥੋੜਾ ਡਿਸਕਸ ਕਰ ਲਈਏ. Processes of absorption of energy by an electron to jump from a lower energy state to some higher energy state is called excitation, and the energy required by an electron to jump from its ground state to an excited state is called excitation energy. For example, in hydrogen atom, the energy required to jump the electron from ground state to first excited state is 10.2 electron volt. On the other hand, the potential difference through which an electron in an atom has to be accelerated so as to jump the electron from its ground state to an excited state is called excitation potential for that state. For example, first excitation potential of hydrogen atom is 10.2 volt. The energy of the electron in the ground state of hydrogen atom is minus 13.6 electron volt. To completely jump the electron from its ground state to a state for which the value of n is infinity. The required energy is E infinity minus E1, which is equal to 0 minus 13.6 electron volt. That is 13.6 electron volt. This is the minimum energy required to free the electron from the ground state of the hydrogen atom. It is called the ionization energy of the hydrogen atom. In general, ionization energy is the energy required to knock an electron completely out of the atom. Mathematically, it is equal to the energy of ground state. This process is called ionization. The accelerating potential of 13.6 volt is required to completely knock out the electron from its ground state. This is called ionization potential of hydrogen atom. आस है कि तुसी हाइड्रोजन एटम दी डिफरेंट स्पेक्ट्रल सीरीज ਅਤੇ एनर्जी ਲੈਵਲ ਡਾਇਗਰਾਮ ਨੂੰ ਚੰਗੀ ਤਰ੍ਹਾਂ ਸਮਝ ਗਏ ਹੋਵੋਗੇ। ਤੁਹਾਡੀ ਇਸ ਅਟੈਂਸ਼ਨ ਲਈ ਧੰਨਵਾਦ। See you next time and goodbye.